Hello everybody. So today we talk about the system design of WhatsApp. So yesterday I talked about this topic and I did the high level design, but I will do the same thing here today for my practice sake. So WhatsApp is the messaging app. So user can create a chat room and the user should be able to send a message and the user should be able to receive the message and they should occur in near real time. So I would specify these as the functional requirements. So user can create a chat space and user can send messages in a chat, hit right to, and other users can receive messages in a chat from other users. And these two things should occur in near real time, which means hundreds of milliseconds typically. So these are the functional requirements. So as the non-functional requirement, I will start with the CAP theorem. So CAP theorem is consistency, which means strong consistency, and availability and partition tolerance. And the system can meet up to two of these. And partition tolerance is a must because we are building this distributed system. So without the partition tolerance, when there is a network loss, the whole system goes down. The system cannot control how to handle it, the network loss. So this P, partition tolerance, is a must. That being said, I have to choose one of strong consistency or availability. And I can rephrase this in a system in this way. So if I take the strong consistency, user should be able to receive the latest message all the time. And if it is not possible as a system, the system doesn't work. The system doesn't return anything outdated. Or if I take A, availability, what happens is that the system always returns the message which is sent, but it can be outdated. Maybe it doesn't include the latest message. So comparing this, definitely I would go with the consistency. No, sorry, availability. So even if the message is outdated, the system should keep working. This is from the decision from the user experience. Of course, for users, it's totally fine that the latest message doesn't appear for a few period. Even with that, he'd like to know the messages. So I would choose availability. Over strong consistency. Next, I would say we need the low latency. So I would say 500 milliseconds for creating chat and sending the message and receiving the message. All should happen in 500 milliseconds. And if the message is delivered within 500 milliseconds, I can say this is near real time. For users, it's almost the immediate message delivery. But let me change a little bit. So message delivery. I changed this because message delivery has two hops. The sender to server and then server to receiver. So I'd include both of them within 500 milliseconds. So that's a low latency. And aside from that, I need the message. I need to guarantee the delivery of the message. So I'd like to make sure that the message is sent to the user. It should never be lost in the process. And also we go with security. So I would say the message is very private information. so it should never be rigged. So for this, message should be encrypted at rest, and also message should be deleted. So we don't want to store the message forever because it increases the risk of the data leak. So once the message is delivered, we want to delete it. And also, if the message is not delivered for 1 month, and if the message remains, it should be deleted. So delete messages. Delete messages once delivered up to 1 month. Okay. Or I should say this. Good. Next, I'd say the what should I say? Scalability. Let me take a look at a node. It should scale to 1 billion data active users. Okay, so this is a non-function requirement we'd like to meet in a system. Okay, next I will talk about the core entities. The core entities are like the table names of the database. So I will clarify the entities which are needed in a system, and then it makes the related processes much easier, like API design and high level system design. And the attribute for each entities, I will talk about this later. Okay, so of course, user sends a message, and oh, by the way, I will add one more requirement here. So in our system, I'd like to make it possible for the user to include the media like images in the chat message. So I include this specification. That being said, we need message and media like image, and image has metadata like the file size, extension, and of course, which message includes that media, or which chat that message belongs to, or something like that. So image metadata is something very important, and of course chat room. Okay. So I think these are the core entities: user, chat, message, image metadata. Okay. Now I will do the API design. So I will clarify firstly the name of the APIs before the specification in detail. So of course, user has to create the chat room. So we need to create chat API. And also user should be able to send messages. So send message API, and also user should be able to receive messages, I should say real-time messages, receive real-time message API, and oh my god, so I also forgot one functional requirement here. So user should be able to receive messages in chat when he's online, and also user should be able to receive hot messages while he was offline. include in this specification here. So for this, we need receive past messages API. Okay, so these are the APIs I need. However, here I'd like to raise some problem. So in this API's, specification, this means that the message is sent with send messages API, send message API, and message can be big, like 5 megabyte, 10 megabyte for images, or maybe for movies, 100 megabyte or something. So before going to doing the API design, I'd like to quickly define and decide where the media should be, stored. And now I also want to talk one more thing. So I defined send messages API and receive real-time messages API. But if I do this, what happens is message is sent by send message API, and the client tries to fetch the latest message by short polling receive real-time message API. But this is not a good design because short polling in a case means that the short polling every 500 milliseconds. This overloads our servers. So instead of that, I would like to use a kind of WebSocket, or I would say SSE, server sent event. I will write it here. I don't use short polling, but I use server sent event or WebSocket. So out of these two options, I would go with WebSocket. I will clarify why it is. So server sent event is based on HTTP request. So instead of the server returns the response immediately, it keeps the connection. And every time server sends a new message, it sends the messages on the connection, arrive connection. And for WebSocket, this is not HTTP. L4 layer is TCP, just the same as HTTP, but WebSocket, this is a kind of bidirectional arrive connection. So server can send a message every time, anytime they want, and so anytime it wants, and client can send messages anytime it wants to. So this is more appropriate in this case because in a case the messages are bidirectional. So client sends a message and server other user sends a message. So because the connection is, the request response relationship is bidirectional, I use the WebSocket here. So that being said, I can actually merge this send message API and number 4 receive real-time message API. So I delete this. So this has a command. Command is a kind of request type. So there is send message command. And receive, or I should say deliver message command. So this is client to server, and this is server to client. And also, as I said, when the message is sent, there should be pre-signed URL to be returned if user try to send the message. So I say notify media you upload URL. Okay. So these are the API commands of the WebSocket. Good. So being said, I will be a bit more specific on each API. So this is HTTP API. So this should be host, chat, and of course we need the authentication of the user. So I will include session token in the header, and the server side can do the authentication, and it can know the user ID. And as a request body, we need the user IDs to be invited into the chat room. Then this should create the API. And maybe we should return chat ID so that the front end can render new chat space in the front end. Next, real-time messaging API. I've written it. So this command should include message, text, and has media, boolean. Yeah. Okay. And of course, we need the authentication. So before the connection is switched to WebSocket, I will do the authentication first. In this way, the WebSocket client has WebSocket object in the server side can be associated with the user ID. So in this way, we can know which user is connected with the WebSocket from our server side. Now, notify media prod URL. We will return S3 pre-signed URL. And for this one, deliver message command. So this is message and has media. And if it has the media, we need media. I should say S3 download URL. And of course, we need which user sent the message. And when it was sent. And of course, we need chat ID. Yeah. So now I have the kind of discussion here from this chat ID. If we should create one WebSocket connection for each user, or we should create each WebSocket for each chat, each user. For now, I will make it one WebSocket per one user and include chat ID here. But this is worth discussing later. The probably is scalability is the main reason and factor of this decision. So I will talk about it later. So next, upload media API. So this is so simple. I just have to do this and download media API. Yeah, this is also same. We don't have anything to include in our API. and we return the media. Of course, there is a kind of resumable upload, resumable download mechanism here, but I don't include that discussion here. And receive past messages. So we need to return like this. And we do the authentication in this way. But again, what is it? So there is one more discussion. So how server side can know which messages should be sent to the client. So here I can do something like, so client has received under this timestamp of the message, and the client specifies the last delivered at timestamp in this request, and the server side returns the messages sent after that timestamp. It is a possible design, but I'd rather not go with this because, and server side keeps track of each user, which messages are sent and which messages are not sent yet. Because here in the security non-function requirement, I deleted this line. Delete messages once delivered. So definitely the server side has to manage and track which messages are sent. So I don't include the timestamp here. I just include past messages, or I should say undelivered messages. And now the server's client side returns the list of messages which have not been sent to the client side. Okay, so this is receive past messages API. Now I will do the high-level design. So I will take a look at each API. So number one, create chat API. So there is a user who would like to create a chat. And this makes the request to the server side. So I will go with the microservice architecture here because, because there are some reasons. Firstly, maybe for scalability, for each server, I'd like to scale independently. And also, I would say it's a kind of availability, or I should say fault tolerance, even if the message is sending, or I should say, even if the feature functionality to create a chat fails, I want the message, delivery of the existing chat to work continuously. So I don't want to make it monolith. And yeah, of course I can say I'd like to separate the services according to the domain to make the responsibility of each service clearer and easier to handle across many teams. So those are the things I can justify for using microservices. But that being said, when the user makes a request I'm talking about create chat API. So chat service, the request is routed into chat service. So this API gateway does routing as well as rate limiting, and I would say authentication. So chat service creates the chat record here. So chat has chat ID and created that, etc. And of course we need user, and of course we need the user chat relation. So this is the kind of relation table. So this clarifies which user belongs to which chat. So I would use PostgreSQL here because obviously we need to run the join query between user chat and user chat relation. So PostgreSQL at this moment works the best, but maybe I will change this database according to the scalability or some other requirement later. So in this way, chat is created and user chat relation is created, and of course these, creating chat record, creating user chat relation records, these will be done in the same transaction. Okay, so next I will talk about real-time messaging API. So we need WebSocket here. So I create real-time message service. So firstly, user makes a request to connect to the server side to start the chat when he opens the chat app. And this firstly is HTTP and then switched into WebSocket. Now, what is it? Yeah. So user sends the message and this should be stored in the database. This is must because some users are not some users are not online when he sends the message, so I have to store the message every time. I will call it ChatDB. So we need message and what should I say? Wait a minute. So ID text and user ID. Then that. So this is firstly stored in the chat DB. And then if this has the image, okay, so client specifies a kind of flag if the message has the media or not here. So if this has a message, this service is responsible for creating the new S3 object, a kind of space where the media should be sent. So after creating the message, this create issue present URL. But I actually want to do this first. Issue present URL first and then create the metadata. Sorry, message data, because if the present URL issuing fails, we don't want to accept the message, and I don't want to save the message as a database because we have to clean up later. So we first issue present URL, and if it succeeds, I continue. Okay, and now here create message and also media metadata. So this media is 3 object key, and of course message ID. So with this message ID, the media uploaded, it can be, associated with the original message. Okay. So in this way, the message and media metadata is created, and now user receives the present URL. So now user directly uploads the file to S3. Okay, and then when it is done, uploading succeeded. Now I have to think how this real-time message service sends the message back to the user. So, okay, let me just don't include this. Here, this real-time message service stores the mapping from chat ID to the list of WebSocket object in memory. So in this way, when real-time message service receives the message in a specific chat, now this service can know which WebSocket he should send the message. So with this, real-time web service sends the message back to the user. Now other users in the chat receives the message, and then they try to download the media. So this is the basic flow of real-time messaging. But of course, there's one issue here. If this real-time message service has multiple servers scaled out, the web server which receives the message may not have the WebSocket connection of some other users in the same chat. So for now, I assume that there is only one real-time message service, but I will talk about how I can scale out later. Okay, now I talked about how user can send and receive messages in real time. The last one is receive pass messages API. This is quite simple. So let me move it. I will call this messages service. So when user makes a request to receive pass messages API, this server receives some request and it fetches pass messages from ChatDB. But as I said, I have something I have to talk here. So I said server-side tracks which messages are delivered to the user. But this system doesn't include that part yet. So I will talk about it. Okay, so now what I can say is server side has to confirm which messages are sent to the client. So the way approach I will take here is adding a new API named Acknowledge Message API. So now client sends the, specifies the message ID and tells that the client it has received the message. And this is the signal to the server side that the message is delivered. Okay. So now in the server side, I will create new entity named message delivery. So let me call it message DB. So this has, this is also the, kind of relation table. So we need message ID, user ID, who should receive the message, and here acknowledged add. So if this is null, this means that message is not delivered yet. So the thing is, when user sends a message, this also create message delivery record here. All of them are created in the same transaction atomically. And now when user receives the message is sent and message delivery is created, and then the other user receives the message and calls the acknowledge message API. Then I will add it to the message service for now. I mean, that API. Then message service flips the flag of acknowledged at, update acknowledged at timestamp. And this is it. Okay. And as I said, we'd like to delete the outdated messages. So if all the messages, for message, if all the message delivery record acknowledged at is filled in, it means that the message is delivered to all the users to be delivered. So we can delete the original message. So we need the kind of cron job to do that. Which is a past message deletion worker. So this worker, this is a cron job, like daily or maybe hourly one. So this, wait. Okay. Now this one makes a request to delete this message. So this is something that happens in the backend. So the message there is deleted when, as I said, message is, current time is greater than sent at +1 month, or all the message delivery are acknowledged. Okay. So I will talk about the database selection here. I will use DynamoDB here Actually, this works with PostgreSQL, but the reason why I choose DynamoDB is DynamoDB scales infinitely. So there should be so many messages which are sent to the server side, and we have to store them in the database. If we store it in the PostgreSQL, when the messages storage size is over 256 terabyte, I have to do the DB sharding. But if we use DynamoDB and let's say specify the message ID as the partition key, it it scales infinitely because inside of the DynamoDB, it scales out with consistent hashing. So that being said, I use the DynamoDB. And if I use the DynamoDB, I will add the redundancy here in the message delivery, because message delivery, sorry. So I mean, like text, adding text here, because message delivery is, I should say, no, I mean, DynamoDB is not good at handling join queries. So it is a kind of, best practice that we have includes the redundancy in DynamoDB table design. Okay, and of course, I will include media metadata IDs too. And maybe we should include S3 object key, blah, 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 for redundancy purposes. Okay, so with this, now the client doesn't have to read message table, but just message delivery table. Okay, so now I will talk about the table design, partition key, and sort key of these tables. So when I design the table schema of DynamoDB, it is a must that we do it by the query pattern. So I will think of the query pattern like, okay, so message, this is not actually fetch anymore because we include the data in message delivery. So I would put ID as primary key. For message delivery, the use case is this API. So receive pass messages API. So with this, all the pass messages whose message delivery is new should be fetched. So, and this is per user. So I make this user ID as partition key and message ID as sort key, because the combination of partition key and sort key must be unique. And we can use UUID3 for message ID. So with this, the message delivery, how should I say? Message ID. Yeah. So message ID, actually, it comes from here. I will create it from UUID3. So with this, the UUID is ordered by the timestamp when it was created. So in this way, messages are sorted by the timestamp. So this brings the message in the UI. It doesn't have to sort it in the front end. Last thing is message metadata. So this one is, how should I say, this is fetched by message ID, and probably I can use ID as sort key, yeah, to make it unique. So message metadata, is fetched per message. When the receiver tries to, from the message ID, all the message metadata IDs are fetched, and then it is returned to the client for the client to fetch the message medias. So primary key should be message ID, and third key should be ID. But maybe we should have kind of media index here, like the index of the media is the same message. So let's say there are 3 images which are attached to one message. In that case, media should have index 0, 1, 2. So maybe I can include that media index in the media metadata, and message metadata ID, or I should say S3 object key return should be sorted by the media index. Okay, so that being said, I finished today's system design practice. Yeah, so tomorrow I will talk about scalability, yeah, and some other security requirements. Yeah. Okay, thank you so much. Bye.